So please ask questions on the course. Post your queries, please. The time is limited. You have to ask questions, and based on that, I'll answer. How many marks the exam will be conducted? I believe it is something like 50 marks. Don't remember exactly, but something around, I think it's a 2-hour exam. So it'll be something like 50 marks. And it'll be mostly along the lines of the tutorial or the assignments that have been given. It's an offline exam, so you have to work out things. Okay, ultimately, probably the choices will be given, not choices. What I mean is that it is some more like fill in the blanks type, where you have to feed in the answer, the final answer. So you'll not be, you don't have to derive anything, you don't have to supply that in the answer paper. But finally, we want the answer, which is either in the form of a number or in the form of an expression, something similar to that. That will be asked in the exam. Okay, so it's neither theory nor MCQ, but you have to work it out and then give the result. Ask if you have doubts about the course. Please ask questions. Okay, I see a question there. Can we go back? Yeah. Devolinagiri, charge density of a superconductor. Somewhere the value of the charge density is 0. Well, assignment marks will be posted in due course of time, in the sense that I'm sure the TA has already evaluated it and will be done. Okay, so let me come back to Devolina Giri's question about the charge density. You see, it's like this, that superconductor cannot have charge inside. Charge means, what we understand by charge is the normal electronic charge. Electronic charge can never be there inside a superconductor, because a charge will constitute a current, and the current would constitute would have a magnetic field associated with it, which is by sort of classical electromagnetic theory. Now, normal charges cannot be found inside a superconductor. It's because if it is found, then there would be a magnetic field, and that is completely not allowed. So the superconductor, the magnetic field cannot stay inside a superconductor. So that's why it is equal to 0. So the charge is equal to 0, charge density is equal to 0 inside a superconductor. It's correct what you said. Conventional continuity equation for superconductors, that's a good question, but there is nothing called a continuity equation for a superconductor. It's mostly, the divergence of J equal to del rho del T is an equation which is either you talk about free space or you talk about a metal. Here we do not have any current, normal current. What we have though is a supercurrent, which is due to the Cooper pairs. So the normal current is now replaced by supercurrent. Supercurrent exists, so there will be a finite density for the Cooper pairs, but not the density of charges, usual electronic charges. So that is what it means. I hope that is clear, Devolina. Okay, pseudo gap. All right, so pseudo gap, Shaumilinath. Pseudo gap is, the gap function of a superconductor, or what we have called as delta, which is energy gap and so on. That is, it's actually a complex quantity, which I've told it during the course. And if it's a complex quantity, you can always write it in terms of an amplitude and a phase. Okay. It's quite important that there is a finite amplitude for the superconducting phase, and it should be a phase coherent state. That is, the Cooper pair wave functions should have a valid, or rather a definite relationship of the phase of one Cooper pair and another. Okay, so there has to be a phase relationship of this phase between one Cooper pair and another. So these two are very important for the superconducting state to stabilize. Now, in general, we don't really need to worry about, for BCS superconductors, we don't need to really worry about the phase part, and we only talk about the amplitude. And most of the time when we have solved it, it looks like a real function, but it is not in general. Now, pseudo gap is a phase where there is amplitude coherence, but there is no phase coherence, which means that there is no definite phase relationship between the phase of one Cooper pair with another. And that's what is called as a pseudo gap phase. So high TC superconductors, the gap function is quite complicated. It is not like the gap function that we have seen for Bcs superconductors, and that is the reason that and that is what is called as a pseudo gap phase. Now, the pseudo gap phase really occurs in the phase diagram in the underdoped region, where if you go up the superconducting dome, that is, you increase the temperature vertically up and be in a regime in the less than about zero point 0.2 doping, that is say 20% doping, then you get a phase where there are pairs formed, but they do not have a phase coherence between them. So they are not really aiding in superconductivity, but they are neither aiding in a metallic state. So it's a very strange kind of state where there are pairs, but the pairs are random in phase, and which is not a superconductor. And then you are, of course, out of the superconducting dome, which means that you are at a temperature which is where superconductivity does not is not permissible to have superconductivity there. Okay, so that is what is known as this pseudo gap phase in the phase diagram of the high TC superconductors. All right. Okay, I think I have answered question thus far. So Devulinas, your question was conventional continuity equation. I don't think there is one for superconductors. The one that you know of continuity equation is divergence of J equal to del rho del T. That is for the J to be arising out of electronic current. I don't think that such a relationship exists for the supercurrent. There are, so there's a parallel between superconductivity and superfluidity. So the superfluid, or rather, I mean, going to the superconducting case, the superfluid velocity or the superconducting velocity or the super electron velocity, so to say, the velocity of the super electrons, they can be expressed in terms of the gradient of the phase that we just talked about. Okay, so that is quite important, and so that is the velocity, and velocity would be related to the current density, but not the current density that you get in the continuity equation. Okay. Okay, Shaumili, in the TJ model, what happens is that when you write down a Hamiltonian, you can write it either in real space or in momentum space. But the problem with real space Hamiltonian is that when you have to solve it, you have to solve it for an infinite system. Otherwise, the finite size effects will come in. Now, when you have a Hamiltonian and then you want to solve it, if the system has translational invariance, now you might wonder that why we are talking about translational invariance, because we have a doped system. But TJ model is a doped system, but we sort of make a, just give me one more. This we get, we need to convert that into Fourier space in order to solve it, because when you convert it into Fourier space, it becomes a Hamiltonian that becomes solvable. And somehow, if you can diagonalize that Hamiltonian by doing some transformation, it's all the more better. Now, the TJ model has a particular advantage, that the J part is the Heisenberg part, which we know, how to solve, and the T part is a single particle whose energies are well defined. So, and then we have only one index, which is K, and we can solve it for a finite. So this k actually is for the infinite system. It's a momentum corresponding to the infinite system. So it can be infinite system means k is 2 pi over lambda, and when you are considering k to be written in terms of lambda, then you actually talk about a system which is infinite in extent, because of the all these the Fourier the translational invariance being there means that we are talking about an infinite system. So yes, the reason for transforming any Hamiltonian into momentum space is that you can find out E as a function of k, which is much easier to solve than solving it in real space, which would require huge computational power to do that. But not every Hamiltonian can be converted into momentum space or Fourier transform it, because there are a lot of things that are important there, because sometimes they may not have translational invariance when you explicitly break them by invoking impurities or defects or disorder and so on. Okay. I hope that is clear, Shomili. So high transmission tower lines, there's because of this large current and voltage, the magnetic field would be very large. So it is not, your body receiving a large amount of magnetic field is not desirable, because magnetic flux lines that penetrate your body, sometimes, when a person falls ill and an MRI has to be done, it is only done once in a while when some diagnostics has to be carried out, but not in otherwise. Always you see that either in an X-ray room or in an MRI room, the attendant of the patient is not allowed to enter, and is kept far away, because there are radiation hazards. Radiations are bad for the body anyway. Cells die. That's the reason. Yes, Shomili, thank you. If you have other questions, please do ask. Thank you, Dasmala. Good question. The applications of ITC superconductors are that, you say, for example, quantum computing, that you might have heard of, that these bits are, made of superconductors, ITC superconductors, which can perform operations which are several thousand and million times faster than the normal bits, and which are called qubits. So this superconducting qubits actually are the backbones of quantum computing, or these what Google had, 2 to 3 years back. They've talked about the discovery of that. So you understand, there is a persistent current in superconductors. So the current once starts, it will go on for 10 to the power 5 years, which means that there is no decay. Because there's nothing to decay. Because usually what decays current, why do you pay electricity bill for? That is because you spend energy in order to keep the fans running and the air conditioners running and the lights glowing and so on. If you put the power off, they will not function because there is no persistent current that we have in our room. The power goes, all the electrical equipment, they stop functioning. But if they are made of superconducting wires, they will carry current on their own. But the only problem is that I mean, even if high TC superconductor, it becomes superconducting only at very low temperature. So that maintaining that temperature is quite difficult and quite expensive affair. Okay, so that is the main thing that even though the advantages are many and we would all love to have superconducting wires and not pay for the electricity and other charges and so on, but it cannot be done because of the temperature being the requirement of temperature is, say, even for the high TC, it's about 70 Kelvin or 100 Kelvin or 120 Kelvin, which is still, at least about close to 80, 90 degrees below 0 degrees centigrade. So that's why it is not so commercially not so viable, but it still has the interesting part of it regarding the physics. And if you ask about the Meissner effect, yes, the high TC superconductor shows the Meissner effect. There are some of the properties which are very robust, and that's why they are taken as an acid test for superconductivity. One of them is, of course, as you said, that Meissner effect. So if you put a high TC superconductor in a magnetic field, high TC superconductors are mostly type 2 superconductors. So they would allow magnetic field lines to penetrate till a certain critical magnetic field, and then after that it will not, it becomes a normal metal. So Meissner effect is obeyed, yes. Please type your questions. So maglev trains are there are the superconducting rails. The rails would be superconducting, and since they are superconducting, they would expel the magnetic field and or the flux lines. So there'll be enough magnetic flux lines. So the pressure due to that, or the force due to that, would be able to balance the weight of the train, and the train will be floating on the superconducting rails, and they will simply not just like normal trains. They have their wheels on the rails. Here it will not be the same. The flux, there'll be an intense magnetic field around those lines, and since they are expelled, the density of the lines will be maximum close to the rails, which will make a train float. Just like that sumo wrestler picture that might have seen in my talk, or even otherwise in the classes, or otherwise it is it'll not sort of move in a conventional sense, but it will float and will glide on the rails. That's what the magnetically levitated trains. Um, Bogoliubov transformation on quasi-particle. You see, any Hamiltonian that you get, the Hamiltonian will have to be diagonalized, right? Because then it gives you the eigenvalues and the eigenvectors, which are most important in any problem. Now, for the Bcs Hamiltonian, which is true even as I said, there's a parallel in superfluidity as well. Then one has a requirement of the diagonalization of the Hamiltonian, and either it can be diagonalized, numerically by putting it into the computer, and then just the way diagonalization scheme works in a computer, such as LU decomposition or Gauss, Jordan elimination and all that. You can see the numerical methods of diagonalizing a matrix. So Hamiltonian is a matrix. So now, analytically, Bogoliubov found that if you convert that Hamiltonian, which is made of single particles, if you somehow write down some quasi-particle operators, which are some combination of the single particle operators. So gamma is some combination of C and C dagger and so on, that is C plus T is C dagger, or AC plus B C dagger, and so on and so forth, where A and B are coefficients. If you do that, then the Hamiltonian becomes a diagonal in the basis of the quasi-particle operators. Now, how does it become diagonal? You have to throw away all the off-diagonal terms. Now, you might wonder that why do I throw away terms when they are there? Now, if you write down the Bcs Hamiltonian and apply the Bogoliubov transformation, you get terms which are like gamma dagger, gamma dagger, gamma dagger, gamma, 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 and gamma, gamma dagger. Okay. So what is important are these gamma, gamma dagger, or gamma dagger, gamma. These kind of terms are only important, and gamma dagger, or gamma, gamma, those terms are not important, and you have to throw them away. Now, when I say that you have to throw them away, that means the coefficients of these terms will have to be put to 0. And when you try putting them to 0, you actually see that they correspond to the definition of these UKs and VKs, which are called as a coherence factors. So they are definitions of UKs and VKs, which means they are automatically satisfied, which means that it is legitimate to throw away the terms which are not diagonal in the gamma operators, because you see that gamma k dagger gamma k is something that you want, because that will give you your Hamiltonian to be diagonal in K, and that's why we do that. So that's called as a Bogoliubov transformation, and why it's called as for the quasi particles, because you are making quasi particles out of single particles. Okay, so they are combination of particles that's why they're called as quasi particles. So they're dressed particles. They're not like single particles, but they're dressed particles, but they have a same anti-commutation relation as the fermions. Did I make that clear? Okay, thank you. Please ask some more questions. Please ask questions. We have about 20 minutes left. Can we get the question that you were showing me on the Excel sheet? Oh, question pattern. Okay, show me Lena. Okay. I have discussed about the question pattern. I'm not so well aware of this, Shomili, but it's a. I mean, I don't know what it means. I've never heard of it. Anderson's pseudospin formulation of superconductivity. I don't know, but it must be the same kind of. If there is something like that, it must be the same as the Bogoliubov theory, that you write down a superconductor Hamiltonian in terms of some pseudospin, and then try to solve this. I know nothing much about it, or rather, I've not even heard of it. What is Anderson's pseudospin formulation of superconductivity? Well, Anderson worked on high-TC superconductor. If you're talking about Phil Anderson, um, but this I don't know. If you can tell me a little more about it, what exactly you have seen, then I can help you on this. It's not making sense because pseudo spin, you need a spin, real spin, for the superconductivity to occur, at least for the S wave superconductor. That is a Bcs superconductor, and also true for high TC superconductors. For P wave, it may not be important. Superconducting material in space, good idea. Uh, but you have to also worry about whether, whether the current will flow there and so on. And if there is a current, then there has to be a detecting mechanism. Or if there is a magnetic flux lines being expelled, then the iron filings. I mean, how do we do this Meissner effect experiment? You take a superconductor, put it in a magnetic field. You know that the superconductor expels all the magnetic field. So the flux density outside the superconductor is maximum. If you put some iron nails or some basically filings, spread it around that region, they will nicely line up because of the flux density that is there. So those experiments, I'm not too sure whether they can be done in space. So yes, at the same time, that temperature is not a problem, but whether super current will flow, that's not very clear. Okay. So it's just not temperature; it's about other things. So temperature is taken care of, but not many other things. The things are weightless there. Detection is a big problem. Many other experiments. I mean, whether magnetic field lines will have any, will be, whether we can detect them and so on. So those are tricky issues. Please ask a question. Okay, thank you. So may I ask Devolina and Shaumili about what are you doing? Like, are you teachers uh, somewhere or your PhD students, etc.? Let me take another question. Pashupatinath Datta and is this Pentium atomic number may be used? I don't know what is this question. UN Pentium atomic number 1. 115 may be used as a superconductor. I've never heard of it. I don't know. Right. Andreev reflection is a very good question. So Andreev reflection happens in the superconductor metal junction. Okay. What's an Andreev reflection? So basically, you have an electron that's coming from the metallic side and it's incidenting on the superconducting side. Or on the superconductor junction. Basically, it's getting incidenting on the junction. Now there is an energy gap of 2 delta, which should not allow or forbid the electron to enter the superconducting junction. But actually one sees that I mean any electron, even with just the Fermi energy of the metal, with that energy it can actually go into the superconducting junction, superconducting side of the junction. And the way it can happen is that there is a hole that is reflected back with its spin reversed. Okay. And what goes inside is actually an electron with, say, one kind of spin, which is a spin up, and a hole which is so there is a vacancy created of one electron going and incidenting on the junction, and there is a hole going back specularly. Specularly means like mirror. And then so effectively there's a charge 2e, twice of electronic charge, that's going inside the superconductor. And this charge 2e is like a Cooper pair. So this Cooper pair can of course go without any hindrance, so to say. So that goes, and that so you get a current even at electron with zero energy. Zero energy means electrons are getting ejected from I mean with energy at the Fermi level of this. Okay. Okay. So is Shomili, is this thing Andreev reflection clear in the NS junction? So so this just the fact that if the electron would have gone and the electron getting reflected, then you would not have a Andreev reflection. But because an electron goes and a hole returns back, so the electron returns back as a whole. There's also an electron that is being reflected back, which will give rise to current in the normal metal. Okay. So in addition to that, what happens is that there's a hole that comes back like a mirror reflection, and these two electronic charge that passes on or carries over to the superconducting side. Okay. I'm glad to know that both of you are doing masters, that is MSc in physics, and from Calcutta University. Okay. So is this course taken into your curriculum as a credit course? Or a special course? How does it work? I mean, all metals are good superconductors, and BCS theory cannot be explained in short, but BCS theory assumes a few things, and it's a theory which is variational. You write down a variational wave function and for the superconducting state, and you minimize it with respect to some variables, find out the energy, and that will give you a superconducting gap, and this superconducting gap seems to be perfect for the BCS superconductor, the magnitude of the gap and the temperature dependence of the gap, and these are the triumphs of BCS theory. Also, by using BCS theory, you can explain Meissner effect and specific heat jump of superconductors, everything. Okay, so that is, but BCS theory cannot be explained in short. Most of the course is on derivation of various things in BCS theory. A good superconductor is BCS type of superconductor is, say, for example, lead or aluminium or niobium, molybdenum, but compounds are better superconductors. Nb3Ac, niobium, selenium, etc. They are good superconductors. Okay. Even more glad to know that you're taking it out of interest and not a credit requirement. Okay. You can write, you have my email ID, so if you have any questions, you could write to me to know more about if you have any questions. Okay. Okay. Yeah. Thank you, Shaumili and Debolina. Any other question from anyone? All right. We have about 6-7 minutes. If you have any other question, you could ask. Thank you. Thank you very much. Yeah, the magnetic levitation is supposed to be Japan would be running it by 2028. That was their original proposal. Japan has anyway high-speed trains, but this would be a completely new technology which they would put it into use by 2028 according to their original proposal. I don't know how it's working out there. um, Actually a lot actually depends on this. The technology is very important. The other things are important in the sense that uh, having a good foundation. Basically, the soil has to support laying down these tracks, etc., and over a large distance. So that's one of the things that is also important, and many other things, of course, and creating very large magnetic fields, etc. See, in India, the scope of having very large magnetic field is very limited, whereas Japan, USA, they have magnetic fields of the order of even close to 100 Tesla. and here even 5 to 8 Tesla is considered as very large magnetic field. Okay, so we do not have such large magnets because magnets are very expensive to run. Yeah. No, no, bullet trains are not. Bullet trains just they have been running in Japan for many years. These are high-speed trains, just about 140 kilometers per hour. They are there everywhere in Japan. Bullet trains are not magnetically levitated trains. Any quick questions? Last 2-3 minutes remaining. There is no superconductor at room temperature, but some things become superconducting under extreme high pressure, which are called hydrides. So look at hydride superconductors, which can become superconducting at room temperature. But that kind of pressure is very difficult to apply, and material whether I mean not all materials become stable at that pressure. Okay, so hydrides are some of them. Any other question? We have less than a minute now. Okay, then I wish you all the very best for your exam, and if you have liked the course, I will be very glad. And if you have any questions, technical questions, that will be yes, please do that. Yes, if you have any confusion on either superconductivity or overall on condensed matter physics, you can get in touch with me. Thank you very much. Thank you.